The next video I want to go through is resonance, because a few of you have asked me already what this is and the relevance of it. So I wanted to just try and give you an idea of what it is and when we use it. So to start with, you need to understand that when you see an arrow such as this, it really is the movement of electrons from there to there. Okay? And if the electrons have moved from there to there, then evidently you will end up with a positive charge where they've come from, and a negative charge to where they're going, because electrons are negatively charged. So if we look at an example, just a simple example, here we have phenol, and this oxygen has two lone pairs on it, and the lone pairs on this oxygen are delocalized around this whole benzene ring. That's just the way it is. And what resonance allows us to do is understand how and where those electrons are delocalized around the ring. And so what you can do is you can push this pair of electrons with an arrow, just like we did over here. But if I did that, you'd end up with 5 bonds to this carbon. You've got 1 there, 2, 3, 4, and the new one, 5. So that can't happen because carbon can only have 4 bonds. So therefore, you have to draw another arrow to take a bond away. So you form a bond and you break a bond. And you form a bond because you're pushing 2 electrons between, in this case, an oxygen and a carbon. And here, you're breaking a bond because you're taking electrons away from these 2 carbons and putting them onto that carbon there. So then we draw a double-headed arrow, because that's what resonance arrows just look like. That's just the way it is. And then we haven't done anything to this double bond over here, and we haven't done anything to this double bond here. So they stay the same. But what we have done is we've broken this carbon-carbon double bond here, and the electrons have moved onto that carbon. And you'll see that when you move electrons, you end up with a negative charge. So the negative charge goes onto that carbon there. And because a bond is made up of a pair of electrons, if we're pushing this lone pair of electrons into here, we're going to make a new bond between oxygen and carbon. So that's the first resonance structure that we draw. And notice that each of the carbons has still only got 4 bonds to it. Remember that we have hydrogens on each of these carbons, so each one has 4 bonds. Then we can do the same again, and on resonance structures you should always try and draw 2 arrows. So here we push in an arrow, but we can't have 5 bonds to carbon, so we have to break an arrow. And again, the structure of that, we haven't done anything to this now, so that stays the same. We haven't done anything to that, so that stays the same. But what we have done is we've broken this pi bond, and we've put the electrons onto that carbon. And here we've used the negative charge and we've made a new bond between these 2 carbons. So we end up with that. And then we do the same again, going round the ring, 2 arrows per resonance structure. And again, we've done nothing to that, so that stays the same. We've done nothing to that, so that stays the same. This time the electrons have formed a new bond between these 2 carbons, and here, to prevent 5 bonds being formed, we've pushed electrons onto that carbon. And then finally, what we can do is we can push the electrons back, and we end up with this. Okay, that's fine, and this really should have been from the negative charge to start with, so we've ended up back where we began. So that's a simple case with phenol. But if you start to stick things around the ring, these charges can get delocalized onto those other groups as well. So for example, if we have this type of molecule here, the lone pairs on nitrogen can be pushed in, and again we can draw two arrows. So we've formed, so we've pushed, we've lost the electrons, so we've got a positive charge on there. We've done nothing to that, we've done nothing to that, we've done nothing to this, and our negative charge is on this carbon here. Now, that negative charge can be pushed around the ring in exactly the same way that it was up here. But in this case, we have a new group. So what can also happen is we can do this contribution. So everything that has been unchanged remains the same, but now we've formed a new carbon-carbon bond, and here we've broken a carbon-oxygen bond and the charge ends up. And then we simply go back again, and that takes us back to here, and then we can push the electrons around the ring just as we did over here. So if we look at the total number of resonance structures that we can draw here, we've got the starting 1, 2, 3, 4 and back to the beginning again. So we've got 4 resonance structures here. Whereas when you start adding extra groups around the ring, it allows you to include more resonance structures. So this has an extra resonance structure. So it has 5 resonance structures rather than 4. So it tells us that the electrons are distributed over more atoms when you have more groups on that ring for the charge to be delocalized onto. And when we, for example, if we look at phenol, if you think that phenol is acidic and it gives you the negative charge, the more groups you have that can soak up this negative charge, the more stable the anion will be, and therefore the more acidic your proton will be. Also, if we do Friedel-Crafts chemistry on phenol, then we know that the negative charge is either distributed here, here, or here, and sometimes on the oxygen itself. So if we add electrophiles to the phenol, we will get reaction either on oxygen, this carbon, or this carbon. We won't get it here and here because in these resonance structures the negative charge is never there or there. So resonance allows us to understand acidity, it allows us to understand reactivity as well. And another example that you are familiar with is a simple amide. So here you have an amide, and it's quite plausible to draw a resonance structure which looks like this, where you've pushed the electrons onto your oxygen and you've left your nitrogen with a partial positive charge. Now notice this bond between nitrogen and carbon is partially a double bond, and double bonds don't rotate. So in simple amides, if you have an amide in a drug, this carbon nitrogen bond here rotates very slowly, and as a result of this resonance structure, the delta plus of your carbonyl is less delta plus in an amide compared to an ester, and that's why amides are more stable to hydrolysis or nucleophilic attack compared to an ester, because your carbonyl is less electrophilic. And so if we continue the argument further, if we have another simple amide, or this case is not an amide, it's a different functional group. If we formed a negative charge, then that negative charge or the lone pair of electrons can be pushed onto this carbonyl and onto this carbonyl in two separate resonance structures. And so if you formed the negative charge on that nitrogen, it's more stable than it would be over here when you've only got stabilization on one carbonyl. So this hydrogen would be more acidic than the hydrogen from the simple amide. And that's resonance.